Hello everyone, welcome to Probability and Statistics for Data Science. In a previous video, we established the celebrated law of large numbers, which states that if we want to estimate the mean of a distribution, we can do so by averaging independent samples from that distribution. As the number of samples grows, eventually the average will converge to the mean. In this video, we show that that is not necessarily the case if some of the assumptions underlying the law of large numbers are violated. And it is often easy to forget that there are some assumptions that we need for the law of large numbers to hold. In such cases, you should not trust an average estimated from data. Let's get to it. We're going to see that the law of large numbers can fail, so in some situations, you should not trust an average. First, let's remind ourselves what the law of large numbers actually states. The law of large numbers says that if we have a sequence of random variables that have mean mu and bounded variance, and we compute a running average of those random variables, so this would be the average of the first n random variables in the sequence, then those running averages are going to converge to the mean mu in probability. What does that mean? It means that for any epsilon, no matter how small, if I look at the probability that there is a deviation of epsilon from the sample mean, between the sample mean and the mean that we're trying to estimate, eventually the probability that there's such a deviation is going to go to zero. Here we see this when we're trying to estimate a population mean from random samples. When we do that, each random sample is distributed in a way that its mean is equal to the population mean, and its standard deviation is equal to the population standard deviation, which is finite. So when we look at sample means computed from n samples as n goes to infinity, each of these points is one of such sample mean, we see that eventually the probability that there's a deviation of more than epsilon from the population mean that we're trying to estimate, which is right here, becomes zero. All the samples are confined to be between plus minus, are confined to be close to the population mean with a deviation of less than epsilon. Okay, so now in this video we're going to see that that situation does not necessarily occur for when some of the assumptions underlying the law of large numbers are violated. In our first example, we imagine that a friend comes along and says, hey, look, let's play a game. I'm going to flip a fair coin until it lands on heads, and I will give you, so the number of times that I need to flip it is k. I'm going to give you a prize which is going to be 2 to the power k dollars. If I flip it twice, I'll give you $4. If I flip it 4 times, I'll give you $16, and so on. Hopefully 2 to the 4 is 16, right? I am prone to make a very silly error, but I think that's true. All right, so then now you're thinking, should I play this game or not? A possible criterion to decide whether you want to play this game is to say, okay, let me compute the mean winnings of this game. Okay, so you can think of this as an uncertain quantity that can be represented by a random variable, the number of money that you will win from this game, and you want to compute the mean. How much money am I going to win on average? Imagine that you don't want to do any math. You decide to go about this in a computational way. What are you going to do? Well, you're going to simulate the game many times, and you're going to see on average how much money you win. But how many simulations should you conduct? You're not very sure, so what you do is you track the mean while increasing the number of simulations, and what you expect to see is something similar to what you saw here when you were trying to estimate the population mean. You expect your estimate of the mean winnings to eventually converge to whatever value the true mean is, and that will give you your answer. But when you perform these simulations, you see something very strange. You see that as you take the sample mean of more and more simulations of this game, the sample means become larger and larger and larger. They do not converge, as in the law of large numbers, to a single value, which is very, very strange. So then you realize that you cannot escape doing some math. So you go back and you compute analytically what's the mean of this random variable that you're trying to estimate computationally. Okay, so what is the mean of the winnings? It's the mean of 2 to the k where k is the number of flips that occur. We know how to compute a mean of a function of a random variable. We plug in the function, and then we weight it by the probability that the random variable takes each of its possible values. What is the probability that we see a sequence of k flips? Well, the distribution of the number of flips is just a geometric random variable with probability 1/2. So that's just 1 over 2 to the k. Okay, so you can verify that the probability of seeing like 4 flips is 1 over 2 to the 4, 1 over 16, and so on and so forth. So now when you compute this mean, what do we see? Well, what we see is that this is equal to 1, so we have a sum from 1 to infinity of 1 that is infinite. So this random variable has infinite mean. This is the St. Petersburg paradox, because according to your criterion, you should pay as much money as possible to play this game, because on average, your winnings are infinite. So should you invest all your life savings on it? Well, probably you shouldn't, because if you think about it, half of the time, your flip lands on heads the first time, and you just earn $2. So what is going on here? Well, what happens is that in some cases, we get a long sequence of flips, and for that long sequence, the winnings are astronomical because it's 2 to the k. Okay, so if you manage to flip like 10, 20 times in a row, you win 2 to the 10, 2 to the 20 dollars, which is a huge amount, and that astronomical amount brings the mean up to the point where the mean actually does not exist. It's infinite because of that. That's why it diverges. But the thing is that those events happen with very, very low probability. It's just that they're associated with such an astronomical quantity, such an astronomical winnings, that drives the mean up and makes it diverge. So that explains why when you compute these averages, if you simulate the game enough, you end up in a situation where you get one of your sequences is actually pretty long within the n sequences here, within the 1,000 sequences, and that drives up the average. But it's just one of them, right? Most of them are going to actually be very short. If you, again, sample 10,000 sequences, one of them is going to be very long and like blow up the average, but it's only one, which again, you're not going to see very often. What's interesting here is that we see a completely practical implication of a random variable having infinite mean. When I was a student, I would often come across situations where the mean of a certain random variable would be infinite, and I really didn't grasp that this has a very practical implication, which is that if you average samples from that random variable, then the sample mean is going to blow up, as we see here. Let's take a look at another example. Here we have a physics experiment, and we're interested in this random variable L, which basically the idea is that you have a source of a particle here that is hitting this line here, and we want to know where it hits the line. And the way we model this is by assuming that this angle is uniformly distributed in minus p halves, pi over 2 to p halves. I don't know what I'm saying anymore. It's Friday at 5 p.m. Yeah, I don't know. Sorry about that. Minus, in Spanish we say p instead of pi. This is between minus pi halves and pi halves. So basically, the angle is uniformly distributed here. Okay, we can see any of these angles with uniform probability. Now what we want to figure out is what is the distribution of L, where is the particle going to hit this line? And in particular, we're interested in where it is going to hit it on average, okay? So again, computationally, what do? We simulate this many times, and we average the position at which the particle hits this line. Oh, and I was forgetting what the motivation for all of this is that we imagine that we actually don't know this location of what is emitting the particle. So what we think is if we we see many realizations of where the particle hits, we should be able to average them and find the midpoint, and that is going to give us an estimate of where this emitter is located. Okay, I forgot part of the story. But the main point is that we want to estimate the mean of L. And again, we could just do this computationally. We could say, okay, let's simulate this many times and take the average of L. Okay, and what we would expect maybe to see is that as we average over more and more simulations, eventually the average is going to converge to the mean of L. In this case, if we put the origin here, you would probably expect this to converge to 0, right? Like, because basically by symmetry, you would think that we're going to get the same, like there's the same probability of seeing L and minus L, essentially, the same density to be more exact. So you would expect the average to be in between, maybe. So let's see what happens. This is histograms of sample means with n equals to 100. If you remember in our discussion of standard error, when we increased n, and we're taking random samples from a certain population and so on, what happened is that this variance was decreasing. And that's also what we see in the law of large numbers when we have this convergence in mean square. Okay, so we have 100 samples. We increase the samples. We expect the deviation to decrease. This doesn't happen when we go from n equals 100 to n equals 1000. Okay, let's go to 10,000. Also not. So what is going on here? So here you see sample means computed with different values of n. And again, we don't see a convergence. If we don't see this graph where I say, okay, like I pick an epsilon, eventually I have to be within this epsilon because the average converges to the true mean. This does not happen, which is very strange. So we realize that again, we cannot just rely on computations and we have to do some math. So we want to compute the mean of L. The way we're going to do this is we're going to derive the PDF, the density of L, and then we're going to compute its mean. Okay, so what is the CDF of L? Remember that often it's easier to derive the CDF because it has an interpretation in terms of a probability. It's just the probability that this random variable is smaller than a certain constant. Well, by trigonometry, if you remember your high school trigonometry, L here is just the tangent of this angle because that side is equal to 1. We're assuming that this emitter is at a distance of, let's say, 1 meter from this line that we're interested in. Okay, so what is the probability that the tangent is smaller than L? The tangent is a monotone function. So this is the same as the probability that U is smaller than the arctangent of L. Why is this useful? Because, well, it's useful because we know that this guy is uniform between minus pi halves and pi half. So now we just have to take an integral between minus pi half and arctang of L, and basically we are done. The CDF is just equal to 1/2, because that's the value for this, plus arctangent of L divided by pi. Now, in order to compute the density, we need to differentiate this. If you're like me, you will have forgotten what the formula is, but I looked it up before the video. This is just 1 over 1 plus L squared. And then we have to, that's the derivative of arctang L. And then we have to also multiply by 1 over pi. Okay, so this is the density of L. Notice that this density is centered at 0 like we had suspected. So we still don't know what is going on because we have this symmetry around 0 that would suggest that the mean is 0. We can compare the distribution. This is the distribution that we just found, by the way, is called the Cauchy distribution, and I'm showing you here in black. We can compare it to a Gaussian in gray. We immediately see that the tails of this distribution are higher than the Gaussian. They don't decay as fast as the Gaussian. And if we looked at this in a logarithmic scale, it's actually quite dramatic. Like these tails that we have just found, they decay as 1 over, in this case, a squared, whereas the Gaussian, they decay exponentially, with actually exponentially of a squared. So that gives us a little bit of a hint. The density for large values for this value, for this random variable, either large positive or large negative values, is much higher than in the case of the Gaussian. Okay, that's a little bit of a hint. But what we really are after is the mean of this distribution, because that's what we're trying to estimate when we compute these averages. Okay, so let's compute the mean of the distribution. We need to integrate from -infinity to infinity a times the density. We're going to separate this into two integrals, and here we encounter something a little bit strange, because in general, what we see is that we have one integral minus the same integral. So what we are tempted to say here is that these guys cancel out, which again makes sense because of the symmetry of the distribution, and the mean should be 0. But that is not the case. Let's see why. Let's take each of these terms separately. When we take those terms separately, we can do a change of variables, t equals to a squared, and we see that the integral is equal to this. Okay, here we just have taken a simple change of variables, and now we can easily integrate this. The antiderivative is equal to log of 1 plus b is just a variable, divided by 2 pi when b goes to infinity. What is that limit? Well, the limit of the log goes to infinity slowly, but it goes to infinity, right? So when we take the limit, this is actually infinite. So we have a situation where the mean is equal to an infinite quantity minus another infinite quantity. Even though these expressions are the same and you would want to cancel them out, you cannot cancel them out if you remember your calculus. The reason is that you could massage that expression to get some kind of finite quantity and then two other quantities that would again cancel out. So you can make this equal whatever you want. So it is not true in particular that it's equal to 0. It doesn't have a value. It just diverges. Okay, so the mean of this random variable does not exist. And this is another example which shows what like computational implications mathematical facts can have. Okay, I said that in a very weird way. What I meant is that as a student, when I came across this situation where some random variables did not have a mean, I really thought it was just a mathematical curiosity. But it's not. It's not only a mathematical curiosity. It tells us that when we compute the average of independent samples from such distributions, then we're not going to see convergence. We're going to see something like this where the mean will not converge. Why is this happening? Well, and it's important to gain an intuitive understanding of it. It's kind of similar to the game situation that we saw a moment ago. In the game, from time to time, we were observing long sequences that blew up the quantity that we were averaging, and that's why the average was higher and higher and higher the more simulations of the game we had. Well, here something similar happens. Okay, so we have our emitter, and it's emitting, it's emitting like the location at which it hits are kind of reasonable locations. But if we repeat the experiments long enough, eventually we get a very large distance, negative or positive. And when that happens, that completely moves the average because this can be really, really large. How do I know that they can be really, really large? Well, we go back here and we look at the tails of the distribution. So this is telling me that there's a possibility of seeing extremely large values. Okay, the tails do not decay fast. It's impossible to see such values for the Gaussian distribution. For the Cauchy distribution, you can see extremely large positive or negative values. And when that happens, the average that you're computing from n samples gets either blown up towards very large positive values or towards very large negative values. And that's exactly what we're seeing here when we look at averages computed from certain number of values. As we increase the number of values, we also increase the likelihood of seeing astronomically large positive or negative values that are going to completely drive the average. And that's why the sample mean will not converge to a specific value, and that's why it's not a mathematical curiosity that this random variable does not have a mean. It has these important computational implications. All right, and now for our last example, we're going to look at a situation where we're estimating a population mean. here the population mean is $2 million. And what we're looking is at gross sell products that basically is a measure of the economic activity within very small regions. Okay, so a certain research team essentially computed the economic activity in many small regions, and the mean of that economic activity is $2 million. So here we do have a situation where the mean actually exists. We're trying to estimate it. Now the total population, the total number of regions is 20,000. What if we want to estimate this population mean from just 100 samples? Because, you know, for some reason we cannot measure it everywhere. We just sample some small regions, and hopefully the mean that we compute from those small regions is actually representative of the whole mean of the population. That's the whole point of estimating a population mean with random sampling. Well, here is the histogram that I obtain when I do this controlled experiment, because in this case I do have the whole population of 20,000 regions. If I only use 100 regions to estimate the population mean, I get this histogram where most of the results are very small, and some of them are pretty large. They're up to $20 million. Compare that with the actual population mean that has $2 million. So what is going on here? In general, what I would have expected from this histogram is for it to be centered at the population mean and have a certain standard deviation that scales with the population variance like we saw in previous cases. In order to understand why it doesn't really look like that, I have to look at the population distribution. This is the actual population distribution of all of these, of the economic activity in all of these small regions. And what I see is that some small regions have astronomical economic activities, and probably one of them would be Manhattan. They're larger than 200 million, which means that if I'm only averaging over n data points, these values can drive the average of my 100 data points by 2 million, which is actually the value of the population mean. So they can essentially double the value that I'm going to see. So what I'm seeing here is that there are extreme values that have such large, because of the presence of extreme values, when I compute averages, the average is driven away from the population mean because I don't have a sufficient number of measurements. Does this contradict the consistency of the sample mean? It does not. If I took more measurements, eventually I would see convergence to the sample mean. What happens here is that the convergence is driven by the population standard deviation divided by square root of n. And in this case, the standard deviation is huge. It's 17.7 million compared to the population mean, which is just 2 million. Okay, so this is a different case from the other two examples that we had in the other two examples. In the first one, the mean was infinite. In the second one, the mean didn't exist. Here, the mean exists, but there is such variance that you have to wait for the law of large numbers to kick in. You need n significantly larger than 100 because of the presence of these extreme values. All right, so what have we learned? We have learned that the law of large numbers does not always hold, and that extreme values distort the sample mean. And in fact, we had already talked about this previously. When you suspect that you might have extreme values in your dataset, you probably should not even be trying to compute the mean anyways. You should compute the median. And in our examples, that would work out. So the median for our game shows that we should definitely not invest in it because half of the time we earn $2. The median for the Cauchy distribution is 0, and that is well defined, and you can estimate it with the sample median. So that would have been actually told us the location of the emitter very well. And finally, the median is a much better measure of economic activity here because it's not completely driven by these regions that have, let me show you the whole population, by these regions that have astronomical economic activities. And that's all I got. Thank you very much.